Hello, Stats 300, and this is Professor Gonzalez, and I'd like to take a look at this homework assignment, which is HW on the assignment side of Alex. This is 5.4, and that is clearly too large of a pen point size. But before we do these problems, there's only 4 in this on the assignment side of Alex. Before we do that, I would like to go to our lecture notes and kind of talk about some of this stuff, the fundamental principle of counting and some things like that. And also I have a formula sheet that I had on the last lecture that is available to you. So let's get started with this. To start this off, let's look at this. It says, if an operation can be performed in m ways and a second operation can be performed in n ways, then the total number of ways to perform the sequence of the two operations is m times n. So that is sometimes known as the multiplication rule, also known as the fundamental counting principle, or fundamental principle of counting. Wow, it's not working very well. And so this is this multiplicative thing that happens. In general, if a sequence of several operations is performed, the number of ways to perform the sequence is found by multiplying together the number of ways to perform each of the operations. We're going to have an example here. And then I think what I'm going to do is show, remember that tree diagram that was on, I think, 5.1. Tree diagrams can be really great for this fundamental counting principle. The only thing is that tree diagrams can grow so large that they're almost impossible to make. But I'll go ahead and make a tree diagram of this situation, this example. But let's first just listen to what's going on here. It says a certain make of automobile is available in any of 3 colors. So available in red, blue, or green. And what else? And comes with engine sizes that are large or small engine sizes. In how many ways can a buyer choose a car? So the fundamental counting principle is talking about these operations, and you can see that the operations right here, there are 3 operations that have to do with color, and then there's 2 operations that has to do with engine size. So here's the answer. There are 3 choices of color and 2 choices of engine. The total number of choices would be 3 times 2 is 6. So when they ask how many ways can a buyer choose a car, there are 6 different ways a buyer can choose a car. So I can show this. I don't have a lot of space. So I have to really kind of zoom in here. But what I could do is, boy, that really does take too much space. These, well, apparently I'm going to have to go all the way down here and try to find a little space to operate. So I can, there we go. So I can have a sheet of blank paper here to work with. So remember I talked about color in that particular problem. So we're talking about the car, and the one choice was color. Okay, and it said there were 3 colors, right? There were 3 colors. What were those 3 colors? I believe a car could be red, it could be blue, or the car can be green. And then there was engine, so this is color. And then there was engine size. So engine size, each of those colors have 2 choices of engine size. And so an engine could be large, right? Or it could be small. So each of those color choices have 2 choices of large or small. And then so when you look at this, when you follow the path of a red car could have a large engine or it could have a small engine. So red car could have large or small. And then follow the path of the blue, and that blue car could have a large engine, or a blue car could have a small engine. And then finally the green car could have a large engine, or a green car could have a small engine. And you can see, there we go, we have 1, 2, 3, 4, 5, 6 different ways we can build the car. And after doing this a little bit, you sort of get the idea, oh, wait a minute, this is that fundamental counting principle thing they're talking about. where if we're talking about color here, that would be 3 different ways, or 3, how many different color choices are there? 3. And then we might say something like, well, how many different engine sizes are there? Well, there's 2. And that's where we can see that 3 times 2 is 6. So you can get there by just multiplying it. Now, I think this tree diagram is nice and kind of shows that multiplication happening, right? We've got 3 items here, 3 colors that end up multiplying out. Each 3 of those get multiplied by 2, and 3 times 2 is 6. Okay, so that is that multiplication rule, also known as the fundamental counting principle. Let's get back over there. Let's see if I can find where I'm supposed to be. I'm supposed to be way back. There we go, back to this page. There we go, come on. Okay, so fundamental counting principle with license plates, with PIN numbers. How many different PIN numbers can you make? Things like that. Here it is. License plates in a certain state contain 3 letters followed by 3 digits. How many different license plates can be made? Now, making a tree diagram with this one would probably, I think, would be nearly impossible. Let's see if we can think this one through, though. And you can see the solution right here, but I'm going to go ahead and just say it in my own words. It tells us that, let's see, what does it say? The first contains the first 3 letters followed by 3 digits. Well, that means there's going to be a letter, and a letter. And then there's going to be 3 followed by 3 digits, digit, digit, digit. Well, how many letters are possible in the alphabet? Well, there's 26, right? 26 letters. So 26 times 26. And then how many digits are possible? Well, 0 through 9, that's going to be 10. And that gets multiplied because of this fundamental counting principle. And so ultimately, we're going to have 26 to the 3rd power times 10 to the 3rd power, right? And when we multiply that, we get 17,576,000 different license plates that can be generated, okay? And so that's quite a few. So obviously, if we were going to make a tree diagram, you'd have 26 branches here, and each one of those 26 is going to have 26, and each one of those 26 is going to have 26, and each of those is going to have 10, each of those is going to have 10, that's going to be 17 million, like 17 and a half, more than 17 and a half million branches on your tree. So I would say that would be near impossible to make because of sheer size and making mistakes. But it's not impossible, but I certainly wouldn't want to try to do that. So we've got this much quicker way by multiplying. All right, let's take a look at the next idea. Permutations. The word permutation is another word for ordering. When we count the number of permutations, we are counting the number of different ways that a group of items can be ordered. The number of permutations of n objects is n factorial. Recall that n factorial, so if someone said, let's say, 5 factorial, and when someone has not had a lot of math, they think that means 5, right? You yell it, you scream it, but no, that's not what it means. It's not an exclamation point. 5 factorial means 5 times 4 times 3 times 2 times 1, and you multiply all that up, right? 3 factorial just means 3 times 2 times 1. And often we don't multiply by 1 because that, the last 1 times anything just is the identity stays the same. So another thing I want to show is talk about simplifying factorials real quick before we get into, because that's part of our formula. So if we had something like, let's say we had 6, try again. Let's say we had 6 factorial over 4 factorial. Some people might think you can reduce out a 2, but it's not going to work like that, because 6 factorial actually is 6 times 5 times 4 times 3 times 2 times 1, and 4 factorial is 4 times 3 times 2 times 1, and when you have common factors, you're allowed to cancel or reduce common factors, and so what you're left with is up top, you're left with 6 times 5 over 1, which is just 30. Okay, so you got to be a little bit careful how you simplify factorials. Another way to do this, which I think works great, is especially when you have a large factorial number. If you have a large factorial number, you can't even put it in the calculator, by the way. So you do need to simplify it before your calculator can even multiply the numbers. But if you had something like, let's say you had 51 factorial over 50 factorial, well, doing it this way up here by showing every single factor is going to take too much time and space. So really what you can do is you can break this down, the numerator, as 51 times 50 factorial. So you just stop when you match the denominator, and you know that 50 factorial over 50 factorial will reduce, leaving just 51. So these are just some tips in reducing factorials. Okay, I think that will work there. Okay, so now let's move on. So an example of permutations: 5 runners run a race. One of them will finish first, another will finish second, and so on. In how many different orders can they finish? Okay, so the number of different orders or different arrangements that runners can finish is 5 factorial. And so it's 5 times 4 times 3 times 2 times 1. And so there's 120 different arrangements or orders that you could, way of ordering 5 runners coming across the finish line. Okay. Another way to think about this, some people like the kind of visual way. And another way is to say, okay, you got a first place. So you got a first, a second, a third, a fourth, and a fifth, right? So how many people can possibly be in first place? What are the choices? There's going to be 5 people that can be in first place, right? Right? There's 5 people running the race, so 5 people get in first place. How many people can be in second place? Well, one of them already took the first place, so there's only 4 left, so only 4 could be in second place. How many people can be in third place? Well, there's 5 people, but one was first and another one was second, so that takes out 2. You're left with 3 people. How many people can be in fourth place? 5 minus the one for first, second, and third, so that leaves, 2? And how many people can be in last place and fifth place? Well, once first place is taken, second place is taken, third place is taken, and fourth place is taken, there's just 1 remaining left. And so that's a way to show, and then we got the fundamental counting principle where we're going to multiply that. And when you multiply that, you get 120, just like we did back here. Let me move, whoops. This is not responding to my touch. There we go. You end up having the same thing as 5 factorial that orders that, okay? All right, and once again, this could be done with a tree diagram, would be pretty challenging. You would say how many people could be in first place, and you would have to have, 1, 2, 3, 4, 5. And then how many people can be in second place, and then each one of those branches is 1, 2, 3, 4, right? And you had to keep on going on, and this thing would end up being this massive tree with 120 branches in the end, okay? So the tree diagram is awesome for trying to understand, not so great when the numbers get large. Let's change this up a little bit. 10 runners run a race. The first place finisher will get a gold medal. The second place finisher will get a silver, and the third place will get a bronze medal. In how many different ways can the medals be awarded? So if we use this particular way, this idea that I had up here, right? Let's use that way. Let's use that technique, the fundamental counting principle. And I'm going to squeeze it right in here. Of course, the blue gives me the answer, but it says how many people? Okay, 10 runners are running the race. We're gonna award medals to first, second, and third. So how many, or gold? Let's say gold. How many possibilities do we have for gold when you have 10 people running a race? Well, you got 10 people that can be gold, right? We don't know who's going to win. Then second place, which is silver. How many possibilities? There should be a V in there, huh? Otherwise it's like sliver or something else. Let's see. Go like this. Let me try again. Silver. How many possibilities? You have 10 runners. Okay, one of them got gold. Now, how many possibilities for silver? There's 9 people left. And finally for bronze, we got a gold, we got a silver, we had 10 totals starting, so we still have 8 left that can possibly be bronze. We're using that multiplicative or the fundamental counting principle, and you multiply, and we multiply 10 times 9 times 8, and we get a total of 720 different possible ways to arrange that gold, silver, bronze when we have 10 people running. Okay, so that's a great way to do it. Let's see, it says we use the fundamental counting principle. There are 10 possible choices for gold. Once the gold winner is exactly what I said, is determined, there are 9 remaining possible choices for silver. Finally, there are 8 left for bronze. Okay. All right, so we should be showing a formula real soon here. So permutations, wouldn't mind showing this. Let me, well, let's read this. Okay, so, and then we'll go to our formula sheet. In the last example, 3 runners were chosen from a group of 10, then ordered as first, second, or third. This is referred as a permutation of 3 items chosen from 10. In general, permutation of R items chosen from N items is an ordering of R items. It is obtained by choosing R items from a group of N items, then choosing an order for the R items. The number of permutations of R items chosen from N is denoted as the permutation of N choose R. That was kind of a mouthful going on there. Here's the formula for us right here. The simplified formula for us. I also have this, as I was talking about, on a formula sheet. Let me just show that. Should show where that's at, what it looks like, if I can find it. There's my formula sheet right there. There's our formula for a permutation. Okay, let's go ahead and use that permutation. And I want to use it on that gold, silver, bronze problem, because I think it's kind of insightful on that one. Now, if you're getting better at this whole idea of the fundamental counting principle, right, we end up getting 10 possible golds, 9 possible silvers, I'm right here, and 8 possible bronze. Multiply it, we get our total of 720. We have a formal way of doing that, and that would be by using our formula for permutations. So this would be called a permutation of 10 choices, or 10 choose 3, I believe. Yeah, 10 choose 3. So what does the formula say? The formula says that the first thing we do is we take this n value. Let me see if I can go back to the formula so you can see it. It is n factorial up top. Remember n, so n is this and n is that little number. So it's the total number of things we're choosing from. So that goes up top. So once again, I guess I'll use a little color there. And the formula says you take 10 and you have to take 10 factorial. And then the formula says that you must take n minus r factorial in the denominator. So use these 2 pieces for that. The denominator must be n minus r. We must use these 2 pieces for that. And so it's going to be 10 minus 3, and that is factorial. Let's simplify this. This is 10 factorial. 10 minus 3 is 7 factorial. Remember how I said to simplify these problems? We're going to call it 10 factorial is 10 times 9 times 8 times, and I'm going to stop at 7 factorial because I've got a nice 7 factorial down below, which will reduce beautifully. And I'm left with, you can see, the permutation of 10 choose 3 equals 10 times 9 times 8, which perfectly matches my 10 golds, 9 silvers, 8 bronze, and I have a total of 720 different ways of arranging the gold, silver, bronze out of 10 people. Okay, so that's how that formula works, and you can kind of intuitively see how it works with accounting, the fundamental accounting principle. Okay, we have another example with a permutation. Oh, and another thing that I need to really, really highlight. I want to go back to my formula sheet because I really did highlight it there pretty well, I think. Right there. And I'm going to use the same color, blue. So permutations, here's the formula that we just did up here. But what's really important is you need to know when to use a permutation and when to use a combination, which we're going to start talking about combinations real soon. But permutations, you're going to use a permutation when order is important, when position is important, when order matters, when you're trying to find, I'm sorry, when order is important or ordered, when you're ordering things, or when you're arranging things, okay? Combination, and that's coming up next, I might as well highlight that, the difference. So a combination is going to be the combination of n, choose r again. The formula is a little different, and I'll talk about that, but use a combination when order does not matter and when you're trying to group things and it's unordered, right? So you're trying to find how many groups I can make of certain things, not taking those groups and ordering them. Okay. Well, let's take a look. Let's take a look. Where am I at? Back there. Okay, so I think what we did was we had another problem here. It says 5 lifeguards are available for duty one Saturday afternoon. There are 3 lifeguard stations. In how many ways can 3 lifeguards be chosen and ordered among the stations? So, so far they're not. So, some of the important wording here is ordered. And does order matter? That would be another question we might want to ask before we know to use a permutation. So far we only know permutations. We haven't really talked too much about combinations. But order does matter here because what is it? What do we have? There are 3 lifeguard stations. In how many ways can 3 lifeguards be chosen? So I'm missing some of this stuff. There are 5 lifeguards total, right? There are 5 lifeguards available for duty. In how many ways can 3 lifeguards be chosen for these 3 lifeguard stations? Okay, so I guess the question here is, if you had station, let's say you had station 1, 2, and 3, and let's say we had Mike, Tom, and Steve. I don't know where you get these names from. So Mike, Tom, and Steve. Would you say it's different? So you got Mike at station 1, Tom at station 2, Steve at station 3. Now I'm still going to use, I'm just going to switch Steve and Mike. I'm going to put Mike here. I'm going to put Steve there. So I'm still using the same guys. But would you say that's a different thing that we have to count? Does order matter here? And the answer is yes. If Mike is on station 1 and Steve's on station 3, it's different if Steve's on station 1 and Mike's on station 3, right? If you flip them around, we'd want to count that because that's a different situation. So this is definitely a permutation where order does matter. So the permutation is, of course, once again, it's just the permutation of 5 choose 3. And so it's 5 factorial up top, 5 minus 3 factorial on the bottom. With 5 factorial, you can write that out as 5 times 4 times 3 times 2 times 1. 2 factorial is just 2 times 1. Reduce common factors just as you would in elementary school. Reduce the 2's, reduce the 1's, and we're left with just 5, 4, 3. And you multiply that, 5 times 4 times 3, and you have 60 different ways of arranging 5 lifeguards having their duty at 3 different stations. Okay, combinations are different, and we'll talk about this probably quite a few times because it does take a little while to really get the sense of the difference between a combination and permutation. But in some cases, when choosing a set of objects from a large set, we don't care about the ordering. We don't care about the ordering of the chosen objects. We care only about objects, only which objects are chosen. For example, we may not care which lifeguard occupies which station. Okay, so in this situation, we got the same question as before, but then they said, I really don't care. I don't care which lifeguard occupies which station. So in that way, you're not going to count. And if that's what you're going to do, then you don't care if Mike is on this one or if Mike is on that one. Just as long as it's just those same 3 people, you're not going to count them as different ways of arranging. And I'll give you another example of that in the future here coming up. We might care only which 3 lifeguards are chosen, each distinct group of objects that can be selected without regard to order. So we don't care about the ordering of them. We just care about the grouping of them, which 3 guys can go on duty. And then they get to pick which 1, 2, or 3 they go to because we don't care. Okay, well, in this kind of way of counting, this is called a combination. And so the formula is a combination of n, oops, that's not what I wanted. The combination of n, choose r, we're going to take n factorial, right, up top. So that part looks the same as a permutation. And then we find that we take n minus r. That looks the same as a permutation. In fact, that is the permutation formula. So what makes this a combination formula is this little guy right here. And so essentially what you're doing is you're dividing out the multiple arrangements using a certain grouping. So I'll try to give you an example of that because it's hard to imagine what I'm saying probably when I'm talking about that. Let's take a look at some examples here. At a certain event, 30 people attended, and 5 will be chosen at random to receive prizes. The prizes are all the same. So first of all, if they said the prizes were different, when you're arranging people, people winning these prizes, so let me finish this. The prizes are all the same. I'm going to highlight that. The prizes are all the same. So that the order in which people, so the order in which the people are chosen does not matter. So what they're saying is, if the prizes were not all the same, like if the first place prize was $1 and the second place prize was $10 and the third place prize was $100, they're all different, then of course who you select and put on that first, second, third, and fourth prize, right, does matter because you're getting different prizes. You might be better. But if all the prizes are the same, then the order that you choose the people does not matter. How many different groups of 5 people can be chosen, okay? And so this is just going to be a combination problem. It's going, because we don't care about the order. So we have, 30 people, choose 5. So up top, we're going to have 30 factorial. Down below, we have 5 factorial using our formula, and we have 30 minus 5 factorial. So this gives us 30 factorial over 5 factorial, and then let's simplify that. What's 30 minus 5? That's 25 factorial. And so they show us how to simplify that. And the step they're kind of skipping by, which I'll go ahead and write in for you, is this 30 factorial, right? Oops, not working. Come on. The 30 factorial, when you break it down, it's 30 times 29 times 28 times 27 times 26 times what? 25 factorial. And then this piece right here is 30 minus 5, which is 25 factorial. So really what they did was they took the 25 factorial, and because they are the same, they are the same factors, they reduced them out. And then where did this come from? Where did this come from? Well, that's just 5 factorial, right? That's where that came from. And then now these numbers are small enough to put on your calculator. You just multiply in the numerator 30 times 29 times 28 times 27 times 26, hit equals, then divided by, and you may need to use parentheses depending on the calculator, probably parentheses, open parenthesis, 5 times 4 times 3 times 2, and then close a parenthesis equal, and you will get 142,506 different, combinations of choosing 5 from 30 people. Okay. So you're going to make 142,506 groupings, different groupings, and that's how they're combinations. Let's move on. Another example of counting in probability. Okay, now this one does get a little bit tougher. This is definitely the toughest one. A box of light bulbs contains 8 good light bulbs and 2 burnt out ones. So let me highlight that. We got 8 good ones, and we got 2 burnt out bulbs. 4 bulbs will be selected at random. Now, let's see. Okay, let me come on. Four bulbs will be selected at random to be put into a new lamp. What is the probability? So we're talking about probability. So now this is different. So what's the probability that all 4 bulbs will be good? Okay, there we go. So this is probability. So I want to highlight something. Previously, we weren't doing probability. We were just counting how many ways we can arrange something or how many groupings we can make. So the combinations are how many groupings we can make, and the permutations are how many arrangements we can make. But so far, they have not asked about probability. So that makes this problem different. Now remember, with probability, you're going to have the events that you're desiring or talking about up top. There's going to be a fraction, right? And then the denominator is going to be the total events or sample space, right? So that's what's kind of going on here. So let's see what happens. The outcomes in the sample space, so this is the total that goes on the bottom of the probability, right? Consists of all the combinations. Now, another thing I think I want to say is why the heck are they combinations and not permutations, you might ask. Why are they combinations? Well, let's think about this. So when you're looking at groupings of bulbs, I guess here's how I'm thinking about it. 1, 2, 3, 4. You want 4 bulbs that are good. Well, I was thinking about drawing a picture of bulbs. That's not a good idea for me to draw pictures. But here's my bulbs, right? There's bulbs. Okay, I can do that. So the thing is, does it matter? So let's say these are all good light bulbs, but does it matter if that was bulb number 1, 2, 3, or 4? Would you consider that a different arrangement if you flip-flopped? Oops, darn it. If you flip-flop these guys right here, if you put bulb number 4 first, and then bulb number 2, and then bulb number 3, and then finally bulb number 1, would you say that's a different setup? You wouldn't, because the order that those bulbs are in doesn't make a difference, because we're just looking for good bulbs or bad bulbs, really, right? So this is just going to be a combination. Let me get rid of that. And so let's see. We're looking for the total, the sample space. And so how many different combinations of bulbs can we have here? So let's see. It's going to be, we got 10 possible bulbs, right? It has 8 good bulbs and 2 bad bulbs. So 10 possible bulbs. And we're trying to pick 4. So this is the sample space. So we don't care. When you're picking 4, you might have 2 goods and 2 bads in there. So we got to count all possible groupings. And so this is just a combination of 10 choose 4, which we go ahead and run through the formula, and we get a total sample space of 210 different combinations, or 210 different ways of grouping 4 light bulbs as we pull them out of the bin of 10 bulbs. Okay. Now, the desired ones that we want, right? We want to, our event is, we want to know what's the probability of this happening, all four being good. Okay, so how many total good bulbs do we have to pick from? And the number of good bulbs we have to pick from is, oh, we have 8. Here it is right here, 8 good bulbs, right? So we have 8 good bulbs to pick from, and we want all 4 of them to be good, right? We want all 4 of them to be good. So we have 8, choose 4. And when we run through that, we get 70 different groupings, different ways to group out picking 4 good bulbs from 8. And when I go back to this model up here, I'm not sure if that was the best way of saying that. Maybe it'd be better if I said, what if you had a bad bulb and a good, a bad, a good, and a good? Does it, if we pulled those out, we don't, in this problem, what we don't want to do is we don't want to count when you have a good, and a bad as something different, because it's a grouping, right? Anyhow, so sometimes, as you can see, this could be a little bit tricky, but so the probability of 4 good bulbs are selected is just going to be the 70 divided by the 210, and we get 1/3. Let's go ahead and take care of our homework. So our homework is way up here at the beginning, and we only have 4 problems here to do. So this should go fairly quick. Let's see. When ordering a certain type of computer, there are 5 choices of hard drives. Okay, so now think about that fundamental counting principle. So let's see where I can actually fit this in. I think I can fit it right here. We'll start with this color. There are 5 choices of hard drive. Whoops, and of course I make that mistake every other time, it seems like. There are 5 choices of hard drive. So let me go ahead and write down hard drive. And there's 5 choices of that. Then what do we have? We have 4 choices for the amount of memory. So memory. 4 choices. And then we go on to 4 choices of the video card. Video card, 4 choices. And finally, 4 choices of a monitor. Finally, 4 choices of a monitor. So, using the fundamental counting principle, and once again, you could make a tree diagram, but it's going to be a pretty dang big tree. But using the fundamental counting principle, you multiply 5 times 4 times 4 times 4, and you get a grand total of 320 ways a computer can be ordered. Okay, next one. Well, can you do a permutation? Well, remember the formula. Where's the formula? Just for your reference, the formula is down here at the formula sheet. We're looking at right here a permutation. Okay, so it's n factorial over n minus r factorial. Let's go back. It is, the formula is, permutation is n choose r equals n factorial divided by n minus r factorial. So that means for this particular problem right here, we want to do permutation of 8 choose 2. So it's going to be 2 factorial all over 8 minus 2. Sorry, not 2 factorial. How did I do that? I don't know how I did that. It's 8 factorial all over 8 minus 2 factorial. So continue to simplify this just so it's a little bit easier to see. 8 minus 2 gives us what? 6 factorial. And now here comes the simplification. 8 factorial means 8 times 7, and you can keep on going, but really the faster way is just to stop and call that 6 factorial, which is true. And that's going to match with our 6 factorial down below. And since we have common factors, we go ahead and reduce common factors, which leaves us with 8 times 7, which is 56. And that's our answer right here, 56. Moving on, how about combinations? Well, the formula for combinations, once again, where do you look? You look on your formula sheet, and here it is right here, combinations. And also, remember, I've got this down here to help us identify. Combinations are unordered groups. Order doesn't matter. Permutations, order does matter. So now we're doing combinations, which is n factorial over r factorial times n minus r factorial. All right, let's take a look. Combinations are going to be n factorial over r factorial times n minus r factorial. So in practice, when we go ahead and put this into our formula, we've got 5 factorial up top over 4 factorial times 5 minus 4 factorial. Just to simplify this a little more, that gives us 5 factorial up top, 4 factorial, and 5 minus 4 gives us 1 factorial. Let's go ahead and set this up for simplification or for reducing. 5 times and then 4 factorial is up top. Notice right there I've got a 4 factorial. And I also have a 1 factorial, which just is multiplied by 1. You see the common factors that, of course, we're going to reduce. So reduce your common factors, and there we are. We're left with 5 over 1, which is just 5. So when we have a combination of 5 choose 4, we just get 5. And there we are, already on our last problem. It says, this is the ice cream question. It says, a certain ice cream parlor offers several flavors of ice cream. You want an ice cream cone with 3 scoops of ice cream. All different flavors. Okay. And how many different, so here's the part. Here's the first one. I gotta look and see how much space this took. Yeah. Okay. Part 1. In how many ways can you choose a cone if it matters which flavor is on top? Wow, that's one picky kid, right? They're saying we want to choose. Let's see, how many flavors are there? Here we go. We got to hit these details up here. There's 7 flavors of ice cream, and we're going to choose. How many ways can you choose a cone? Let's see. Well, the rest of it. So there's seven flavors to pick from. You want ice cream cone that has 3 scoops. All different flavors. And you got the pickiest kid in the world. It matters which flavor's on top and so on, in middle and bottom. Well, if order matters, then this has to be a permutation, meaning the kid's going to throw a fit if you had chocolate. So let's see. I want to show some stuff here because I think it will help with the idea of permutations and combinations. This first one's going to be a permutation. This first is going to be a permutation, and what is a permutation? Well, let's use our formula, then I think I'll draw some pictures if I can. So if this is a permutation, basically what we're looking for is 7 choices, and we want 3 scoops of ice cream, and the order is important for this picky kid. So it's going to be 7 factorial up top, and then we've got 3 factorial times 7 minus 3 factorial. Let's simplify that just a little bit. We got 3 factorial in the bottom, and this right here, 7 minus 3 is 4 factorial. And let's simplify a little bit more. I got 7 times 6 times 5 times 4 factorial, and I just picked my biggest factorial so I can get, the biggest bang for my buck in terms of simplifying. So I just reduced the 4 factorials. don't forget you still have 3 factorial. So I'm going to write that out as 3 times 2 times 1. And so now all you have to do is, oh, I totally screwed this up. Gosh darn, I am messing up today. Sorry about that. The permutation does not have this part. That's a combination. So it does not have this part right here. And once again, I'd like to say that I did this to test you, but I'm just sleepy. It's late again. So anyhow, that's our permutation. Let me just reiterate that. The formula for permutation, if I get my pen to work, the formula for permutation is n, choose r, and it's going to be n factorial over n minus r factorial. And so all we needed was 7 factorial up top, 7 minus 3 on the bottom. So there we are, and now we're left with 7 times 6 times 5, and 7 times 6 times 5 is 210 different ways that you could arrange 3 scoops of ice cream on a cone, given that you're selecting from 7 different ice cream flavors. But this is the part that I was thinking about, and I guess I kind of got messed up on my formula for a second there. But I wanted to I'm trying to think about a visual way of showing this, and so my brain was thinking, I was trying to be a teacher. So I was thinking about what can I draw to show this, and so I couldn't help but think about these little ice cream cones. Maybe I'm getting hungry too, so I got distracted. But let's just look at 3 colors, probably the most popular kind. How about vanilla, chocolate, and strawberry? So let's say there's a vanilla, a chocolate in the middle, and a strawberry. So with a permutation, this is the picky kid, right? Order matters. How many different ways can we count this? I'm thinking it this way. I'm thinking, okay, I've got strawberry on the bottom. So I'm going to keep that fixed. And so we've got strawberry, chocolate, vanilla. So how about strawberry, vanilla, chocolate? That's another way. And then what if I put vanilla on the bottom? And so I could have vanilla, strawberry, chocolate. And how about if I had vanilla on the bottom and I had a chocolate and strawberry? Okay, what else could be on the bottom scoop? Strawberry, vanilla, chocolate, right? So I could have chocolate, strawberry, vanilla, but I could also have a chocolate, vanilla, strawberry. So just with those 3 colors, we're coming up with what, 6 different ways of arranging just those 3, not colors, 3 flavors, right? Okay, let's take a look at the next one. I think hopefully this will give you some insight of the difference between permutation and combination by my silly little drawing right there of ice cream cones. The next one is saying how many different ways, so let's highlight, how many different ways can you choose a cone if order of the flavor does not matter? Now, what does that mean, that order does not matter? Well, it basically means that if we're looking, gosh, drawings are getting worse by the second. Should be a little bit more, there we go. So if we're talking about an ice cream cone and we're talking about vanilla, chocolate, strawberry, those are the flavors of the 3 scoops, that's all you count, right? Because that's the grouping of those 3 flavors. If someone said, well, wait, isn't a strawberry, chocolate, vanilla, isn't that different? Not in the world of combinations, that's not different. We would not count that. So notice the reason why combinations are always going to be smaller is because we're counting vanilla, chocolate, strawberry as just one arrangement, whereas with permutations, with vanilla, chocolate, strawberry, we're counting that as 6 different ways of arranging, right? So that's why this is thought about as grouping, because you're counting how many different groups can you make with 3 different flavors, whereas over here you're talking about arranging those. You've got this grouping of 3 flavors, but now we're going to arrange them, so order matters, right? So order on this one, order doesn't matter. And over here, order does does matter. Okay, so we can see that the combinations should be a much smaller count given the same situation. And so we have the same situation. Here's number 2, but this next one's going to be a combination. Next one's going to be a combination. All right, so what's the formula for the combination? Well, the formula for the combination is a combination of n choose r equals n factorial over r factorial times n minus r factorial. And like I was trying to show before, the difference between permutations and combinations is this gets divided by r factorial. Well, if you're dividing by a bigger number, you're going to have a smaller outcome, right? It's going to make this outcome smaller. Let's see what happens here. So the actual problem here, it said the same situation. We have 7 different flavors, but now it's going to be a combination of 7, choose 3, and we don't care the order of the ice cream flavors on the cone. So it's going to be 7 factorial over 7 minus 3 factorial, which gives us 7 factorial over 4 factorial, which gives us 7 times 6. Oh my gosh, now I'm doing the same thing I did on the last one, but the opposite. I forgot my 3 factorial. I should just start over again so you think I'm perfect. No, I guess not. That's out the window. So now we've got we've got our combination of n choose r, remember? So we've got 7 factorial up top, we've got 7 minus 3 factorial, and then we've got this 3 factorial that I made such a big deal about. And I said this 3 factorial is going to make this number smaller because you're dividing by a bigger thing in the denominator. And then I didn't write it down. Just lost my brain completely for a second there. So anyways, there would have to be a 3 factorial right there. Okay, so let's go ahead and simplify. 7 times 6 times 5 times 4 factorial. That's going to match up nicely with my 4 factorial right there. And then let's not forget my 3 factorial, which is just going to simplify out to make what? 3 factorial just means 3 factorial, just means 3 times 2 times 1. So, of course, beautifully, like most of these problems, 4 factorial over 4 factorial will reduce out. And then now, when you look at the numerator is still going to be, what? 7 times 6 times 5, and we did over here and got a 210, so it's going to be 210 up top. But the difference with the combination is we have to divide it by 6, which is going to cut the different ways of ordering this down by quite a bit. In fact, it cuts it down to 35. We can make a 5 a little better, 35. Okay, so with combinations, you're only going to have 35 different ways of ordering 3 different of grouping, I should say, 3 different colors when order doesn't matter. But when it's a permutation and you've got 7 choices of flavor and you're going to select 3 at a time, when order is important, you're going to have quite a bit, many more ways of arranging 210. Okay, and I think I better pull the plug on this particular talk here. And I hope you're having a great day and talk to you soon. Bye.